With the story that we were uncovering on Saturday. So let me just remind you of the thing we ended with, which was quite remarkable last time, which was this statement, which we gave the name T-duality. What I've written here is just a summary of some of the key facts going forward. So we take a 10-dimensional closed string theory, and we study the simplest compactification that you can think of, which is just to put the theory on a circle. So I end up with this 9-dimensional uncompactified theory, and we looked at the mass spectrum in those 9 dimensions, and there's the usual contributions from oscillators. But then there's this very interesting thing that's going on, which is that there's these two sectors which contribute states that depend on R. There's the fact that I have momentum in that x9 direction, and x9 is now a closed box, so particle in box tells you that's quantized in units of 1 over R. But then I also have the fact that the string can wind around the circle, which is a new feature, which is different from the Kaluza-Klein story coming from the momentum sector. And that winding means that I have now a new family of states corresponding to how much the string has stretched. It costs energy to stretch a string around that 2 pi r circumference, and so there are new families of states corresponding to winding states whose energy goes proportional with r. What that meant is that as you try and do what you would think you would lead you to a purely 9-dimensional theory, shrinking that circle away, actually the winding states build back up that 9th spatial direction and takes you back to 10 dimensions anyway. So the conclusion is that an R goes to 0 limit turns out again to still be an R goes to infinity limit. But it's really an R primed. The radius of that effective new circle is, if you like, the inverse radius, and so that's a relationship then, which we saw precisely in the mass formula. If I replace R by R prime according to that relationship, I exchange winding and momentum, I can see that I have the identical theory. So the theory just keeps taking itself back to the uncompactified theory in either of these limits. That's hugely important. And then, as we saw in questions, something must be different about that story if we start considering open strings. So we found the new phenomenon. Let's try and understand it in various other areas as we did before. So you might ask, what happens with open strings? That's what we're going to talk about today. But before we do that, I want to just briefly talk about another piece of language that we use a lot in study in string theory. You may have done this with Barton or Carmen earlier last week, but I want to make sure that you've seen it so that other lecturers can use it, and we're also going to use it later on. So let me just talk sort of briefly the low energy effective action. Right, which loosely everyone just calls supergravity. Okay, so did you do anything about that? Yes? One person? Okay, more than one person. Okay, so I'll just briefly summarize, but here's the logic, okay, just so we're all clear. We saw it explicitly in our mass spectrum. Let's now talk about our 10-dimensional mass spectrum where we, sorry, mass, where we had essentially, I'm just going to be schematic here because the factors aren't important to make the point. Okay, we had some things that essentially just counted counted the number of oscillators, some sort of number operator. This is just the bosonic piece, and then some number here, 1 in the bosonic case, half or 0, which I think we just call A. Okay, and then we built states. We built states by exciting with oscillators. Okay, we built up the massless sector of the theory, but of course we observed that there's more than a massless sector. There's an infinite tower of states. I can just keep adding oscillators and so on and so forth. But the point is that there's a very nice feature of this spectrum that allows us to organize things rather nicely, and it's the fact that I have the massless sector here, the massless state. So G mu nu, capital G mu nu. So the graviton, for example, and of course the various Ramond sector states we talked about as well. Okay, and they're all down here. There's also the photon, or the Yang-Mills sector in general. But the point is that there's a gap, right? There's a nice separation in energy between that massless sector and the remaining infinite tower states. So you can imagine your field theory intuition tells you that there ought to be a very nice procedure in which I could write down some effective theory of these massless fields in space-time, where I'm looking at energy scales low enough so as not to excite these explicitly. So in some sense I've integrated them out of the theory and then written some effective theory just for the massless sector. And so that's one way we think a lot about what we're calling the string theory. And sometimes we use the sloppy term that we write down some 10-dimensional effective action, which I'll remind you of in a moment. And people sometimes say, this is string theory, and it isn't really, right? It's all the things I just said, right? Are implicit in that. But nevertheless, it's an extremely useful tool to write down, and in some sense helps organize several of the pieces of language that we're going to use later on, and that you'll use in other classes. So there are many different approaches to how you would write this down. So you could simply write down the simplest action you could write down based on just having a derivative expansion looking at the lowest order. You'd expect to write something like Einstein-Hilbert and then couple in these other fields, and then knowing how much supersymmetry you have, for example, could actually help you write down the rest of the action completely. So that's one approach. The approach you may have heard about in other classes is also maybe to write down a sigma model. Did you hear about that? Yeah. Right. So you write down some effective two-dimensional action. You go back to the string theory itself and say, well, I ought to have some action that looks like this. There's some two-dimensional story, okay, and then I write down something like the Polyakov action that we had before. Okay, and then in the background associated with these fields being turned on, I would expect some induced couplings, which, of course, because G has some background and can depend on X, are highly nonlinear, of that sort of structure. I guess I should be more careful here. There's also there's also the two-dimensional GAB. I should write down, and that's a moment. And then what I would do is I would try and ask that the story we had before, where we asked that this is a conformal field theory, we do that again. So that's going to put some constraints on the G's, because this is now some two-dimensional theory with some highly nonlinear couplings, and I want some information about how those couplings are constrained. And so that's going to be what I call the beta function conditions. Will give us some information about G and its derivatives, which will be the two-dimensional condition that I have a conformal field theory, and also B and phi and all the other fields. But then the great thing is that that two-dimensional perspective also, as I've told you several times, also has a 10-dimensional perspective, because it'll be a set of equations involving G and derivatives of G, which, due to the way you've written things in a Lorentz covariant way, means that you'll always write down space-time Lorentz covariant information about G and its derivatives. Those derivatives will organize themselves into things that you're familiar with in terms of the Riemann tensor and things like that. But at the end of the day, you're going to write down space-time equations of motion that will generalize the space-time Einstein equations. And so that's the logic of the whole story. And so I'm just going to write down now the 10-dimensional action that would give rise to those 10-dimensional field equations. So just to repeat, you write down this beta function equation for asking for conformal invariance of these couplings. So I'm sure you've seen this before. There's also a coupling for B. Let me just schematically write it down for you. So there's a similar thing here. This is the two-dimensional antisymmetric tensor, which makes you write down a sensible coupling. And then there's a coupling to the dilaton as well, which actually couples to the two-dimensional Ricci scalar. And there's a few factors not quite right, but that's the structure of the story. And then you'll also then have things involving B and phi and derivatives of those fields as well, which I then interpret as the 10-dimensional space-time equations of motion. And then I can write down an effective action for that would give rise to those. So that's what I say when people say they start with a 10-dimensional supergravity action and often say this is the string theory. They don't really mean that. They mean all of this. Right? And so that, it's a long story, but it's an important one to keep in mind. That's where that all comes from. So let me write these down, because they actually are going to be important for us, and there's a couple of observations I want to make as well. Are there any questions about the logic of this story before I write down the results of all of that hard work? Okay, so let me try and keep them up here so I can reserve this board for later things. So. Scrolling back a little bit, excuse me. I've lost where I wrote down those actions, excuse me. I was going to do this last time, but I wanted to get to T duality. Okay, yes. So, type 2A, I'm going to write down a number of quantities that I will explain in a moment. So an effective 10-dimensional action, then there's the leading stuff will look so there's Einstein-Hilbert. I'll explain a little bit about this scalar piece in a moment. Okay, so this first piece is common to both of the superstring. So I can write this for type 2A and B. Right. So what comes next will be different because, as you recall, the content in the Ramond-Ramond sector is different. So I have some 10-dimensional metric G. So I have the usual det G to the half. I have the Einstein-Hilbert term here. I have some two derivatives on a scalar, as you might think you ought to have, with perhaps an unusual normalization. I can talk about that in a moment. And then I have a field strength term for a three-form field strength, the fifth being the three, H rank 3 is the field strength of our friend, the antisymmetric Karl-Ramond field. Okay? So one of the things I wanted to point out here before I write anything else down is that this is often referred to as the being in the string frame. And there's a lot of, one could spend a lot of time explaining what that means, but very briefly, when I have a scalar floating around in the theory, I get to rescale what I call the metric, right, for free, and essentially the normalization you're familiar with from general relativity is where you just have would have just the Einstein-Hilbert term with no prefactor, and then if it's coupled to some scalars, they have more canonical normalizations. There's a reason, which will take me too long to go into, where there's a nice choice of frame in addition to the Einstein frame, which is called the string frame, which has this e to the minus 2 phi power in front of it. So I'm going to explain in a moment why that's extremely natural, and it's going to actually help us organize a number of observations later on as well. So actually, let me say it now. So let's go back here and look at this string action, string theory action. And if you recall, the dilettante has something to do with the strength of the coupling, how controlling the strength of the splitting joining interaction of the string theory. You maybe were studying that in. Did you study string interactions at all in any of last week's classes? So the dilettante is somehow some local measure of that strength of splitting and joining. And one of the rather nice things, ways of seeing that, is the fact that string perturbation diagrams are organized by topology. Right? So essentially, everything I can do with the closed string and also the open string in terms of joining and splitting strings at various orders of perturbation theory boil down to just counting at what order of topology am I in the string world sheets. And particularly for closed strings, I'm simply counting once I take the external states away. I'm just counting what's the Euler number, what's the number of handles that a diagram has. So torus has one handle, and so on and so on and so forth. Well, here's a nice thing. If you look at this, the dilettante is essentially locally coupling to the Euler number. The Euler number in 2 dimensions is 1 over 4 pi. Right, the topological invariant that's playing a role here is is this. Okay, and you can see that the dilaton is, so I think I've normalized this correctly. This is the Euler number. And the dilaton is actually coupling to Euler number. So the dilaton is in fact telling us how strong the string coupling is. Remember, this whole thing is exponentiated, e to the minus s, right, in computing amplitudes, etc. So e to the dilaton, so the local string coupling g subscript s is essentially set by e to the, I'm going to check my signs in a moment, I think I have this right, the local expectation value of the dilaton. Have you seen that before? Was that something that was discussed? Yeah.
GLD has to be inside of the scope.
Oh yeah. Oh yeah. Thank you.
There's no J.
I'm not hearing. Sorry.
GLD.
Okay. So
So that's the rich two-dimensional tensor, right?
No, I like that there's no GAP.
oh yeah. Thank you. Yeah. Yes. Thank you. Yeah. Yes, but clearly that expression was nonsense because there was an A and a B just flapping in the breeze. Yeah, not good.
I have a question.
Okay, where am I looking? Yes.
When you do the equations of motion for the dilaton field, you get that the curvature will be 0.
Curvature of what?
The R supra 2.
I don't understand.
If you do the Euler-Lagrange for the dilaton field, you get R equals 0. Even
Phi is not a dynamical field. Your fields are X.
como
Las ecuaciones de movimiento tú las calculas para X. Aquí son los campos de Wolf. Estos son las configuraciones funcionales de campos físicos de
y phi no es una variable dinámica.
No.
I didn't understand the question, and I definitely didn't understand the answer. So I'm going to move on.
The question was, the problem was that the phi is not a dynamical field, right?
Oh, right.
If phi was a dynamical
Yeah.
field,
Yeah, these are couplings.
It's couplings, right?
Yeah.
It's only X is there.
These are 10-dimensional fields. In the two-dimensional action, they're just a given coupling that the string inherits from moving in that space-time with those fields turned on.
Okay.
Yeah.
I thought it was
Okay. So now I understand the question. Yeah. Okay. And yes, so that's correct. And so yeah, and so this is, for example, 2 minus 2h, the number of handles, and it'll generalize to the full order number when I have boundaries in the surface as well, corresponding to open strings. So just to finish this point up, then, you know, from the point of view of string perturbation theory, we'll have, you know, for example, this diagram here. What you could think of as there's three operators which correspond to inserting these incoming strings, and you compute your amplitude, and you know, it's essentially at that level of perturbation theory, and so on and so forth. So you build up perturbation theory in this way. And you know, that's a very long story that you may not have seen a lot of because it's a whole course in and of itself. Anyway, so if you, in your spare time, draw your favorite diagram and count the number of handles and see what order of perturbation theory you're in. and so on and so forth. So that's how it works. Okay, all of that was just to allow me to go, oh look, this, one of the reasons you can see that this is a good frame to be called the string frame is because this is at order then G string to the -2, which is, I did that wrong, G string to the 0, G string to the -2, etc. That's the sphere level, that's tree level in string perturbation theory. And we've been doing tree level at string perturbation theory in deriving this basic spectrum of the free non-interacting stuff so far. And so it makes perfect sense that there should be a frame in which those fields associated with, those terms associated with controlling the kinetic terms of the graviton, the dilaton, and B is controlled by a term which is all you can read off at order G string to the -2. Does that make sense? At least morally? Okay, so that's an important piece of organization of how string theory works, which shows up all over the field. And I did think it was worth spending a bit of time talking about that, because you're going to see it in so many places that you should know about that. Okay.
Sorry.
Yeah.
Normally, you would think that there is some kind of solution with phi equals to 0.
With
some kind of background solution with dilaton equals to 0.
They exist, yes.
So what happens with the string constant in that case? Because it would be 1.
Well, okay. So there's a more careful story that I could go into now. Let me say it now. Then, in some sense, the local expectation value of the dilaton. There you are. Thank you. The local expectation value of the dilaton you can think of as some sort of measure of the effective string coupling. What if I'm more careful? Let me be more careful. If you look at how the dilaton appears everywhere, there's actually a freedom to. There's really a sort of background value of the dilaton that I had turned off in that discussion that I should really turn on to. Essentially, if you like, you can think of it as the asymptotic value of the dilaton in some background. I'm going to call that phi 0. And so if I'm more careful, I should really look at that. Once I've normalized everything correctly, that really I should think of as telling me what the overall background value of the coupling is. And then any amount of dilaton above or below that adjusts the coupling one direction or the other. So when I take into account phi 0, so if you like more carefully, let me call this phi 0 then as setting the value of G string. Then I have two, I can pull that out, and for example, you can see how it works here. If I have that phi 0 here, but I actually bring it out and put it into here, this, if you remember, is setting the value of Newton's constant. And so you can see then that 2 powers of that dilaton also show up in setting the strength of gravity, which is, splitting and joining of closed strings. And so perhaps that's a more refined way of keeping track of what you just said. So take your favorite solution of Einstein's equations, lift it, say, to 10 dimensions, write that down, and it'll have some constant value of the dilaton, but you need to set that by from some other place to know what that phi 0 is. So, okay. Thank you. Okay, so that's my fault for being a little sloppy there. Okay, so in view of the time, I'm going to quickly then just tell you the remaining pieces of the actions here, and then we're going to revisit, we're going to go back to our T-duality story. So for type 2A then, clean this up. the type 2A, I have, now looking at the Ramon-Durand sector, the other fields, remember I said that I was going to call their field strength G. They were the fields themselves were C, so in type 2A I had a 1 form, I had a rank 1 guy, 3, etc. Okay, so I'm calling their field strength G with the additional number in the rank. And they look something like this. Okay, and one of the things to notice here is that there's no power of e to the minus 2 phi, or e to the minus anything phi in front of the, well, okay, 0. Okay, and that's also telling us something about how we get these terms in this effective string story. You do not get the Ramon-Durand fields working in this way. In fact, in traditional string theory, there's no way of seeing how to get them from a sigma model description. So here you can get them because we know how to complete it all due to the n equals 2 supersymmetry that we have in 10 dimensions. And then there's a sort of Chern-Simons type coupling as well, which looks something like this. It looks something like this. That's a wedge. Okay. You know, I wouldn't stress too much about writing all of this down right now. You know, you can look it up as needed. But it's important just to get a sense of the structure of these things.
So that,
Sorry.
Yes?
that doesn't couple to graph.
It's what do you
We
mean?
have like the square root of minus.
It's a Chern-Simons type coupling, so that's all there is, yeah.
Sorry,
Yes?
these fields are not coupling with the dilaton.
Yeah, I just said that.
I didn't.
Okay.
Okay, thank you.
Yeah, and it's true and it's important, and yes. Okay. 2B has a similar sort of thing at the start, remember? Let me not write that out again. Then there are terms, you know, I'm not going to need this. I'm not sure anyone's going to need this. So I'm going to say glibly either look it up or do the supersymmetry variations and derive it yourself. Okay. So I'll just say there are things involving, you know, G5, G3. No, yeah, that's right, etc. Okay, so forgive me. You know, I can just write a whole bunch of stuff down, and why do that? We're not going to need it. But the last thing I wanted to mention then is that there's a specific value of that number, right, which ultimately will set Newton's constant in 10 dimensions, and we will need that. So let's actually work it out. Not work it out, write it down. So how would you work that out? You need to know the strength of the strength of gravity in 10 dimensions. So you can actually do some graviton scattering with the real string theory and actually compute what the effective G is, and that will be, you know, 1 over 16 pi G Newton in front of here. So it should be something that's given entirely in terms of string theory parameters. And so let me write it out for you. As I promised, with the appropriate definition of phi 0, the background value of the dilaton, it's going to also have a G string squared involved. So that defines 16 pi G Newton in 10 dimensions. And now there's some real numbers I need here, which are going to be important. Right, there's specific values of the constants. of the physics. So this alpha prime raised to the power 4, as it should be just for dimensions, the right length dimensions of Newton's coupling, and then there's a 2 pi to the 7 in the conventions that hopefully now everybody uses. Okay, so that's going to be important later on. So that's set by the fact that I have definite normalization for what my strings are doing in the basic string theory. Okay, so I could also write down an action for the type 1 theory, right, involving, and you could get it in the way we did before. You start with the type 2b action, you throw out all the omega equals odd fields, and then you add in that SO32 sector and some of those green-Schwarz couplings that I was alluding to. And again, I'm not going to need this explicitly. I believe in your course on dualities, you will have this explicitly given to you. But the logic is not so different from what we talked about just now. Okay, so yeah, there it is. So let's at that point return now to the guts of the string theory discussion to try and understand T-duality for open strings. Are there any other questions about it? Yeah.
Yeah, I'm just wondering about the physical content of this action, like type 2A. So you have gravity, pressure, dilaton, scalar, and this H will be an antisymmetric tensor. What does it describe, like physically? Because it's not a photon, right? The photon is in type 2-1.
That's right. It's a space-time. So all of the I have B. H is the field strength of B, and I have the G's are the field strengths of the C's, and they're all just antisymmetric tensors that are allowed to live in space-time and move around. Now, we've already got an interpretation for B. Remember, B really is essential for a closed string because it's the thing that naturally talks about the winding of the string. Okay. And here's another perspective. If I look at this up to factors that I may have, maybe there's, depending upon how I've written this, there may be a factor of I here or something like that. But if I look at this, let me write this term out properly. Another way of thinking about this term is that it's the natural thing that you would write down that generalizes. What am I looking for? An eraser. Okay. It's the natural thing that you write down. As soon as you start thinking about extended objects, you go back to how you think about point particles, and you go, what would be the natural things I would generalize? Okay. So if I were writing down a point particle that was charged under some one-form gauge field, okay, there's something I know that I would naturally write down, which is as the particle sweeps up a world line, okay, there's a natural thing that I can integrate along that world line, okay, and it's essentially the fact that I have a mu, and if I parameterize this thing with tau, I have a dx mu, a mu, dx mu, d tau type term I can write down. Yeah. And if you like, that then has some coupling, which would be the charge of the string. Sorry, just blew my punchline there. Charge of the particle to this guy, the coupling of that to this guy, right? And so we've all done this, yeah. In some sense, another way of thinking about B is that's precisely what it's doing, right? If you look at it, there's a string, the closed string sweeps out a world sheet, I need some two-dimensional anti-symmetric thing, which would be the natural, which would define the natural form that I would integrate on that two cycle, right? And so that would be integral B, written in form language, but if I want to do the whole story, it's B mu nu dx mu dx nu. But now I don't have just tau, I have sigma. We don't write out all the terms, let me just put A, B, epsilon A, B. It's this interaction. Yeah? So you've just like in our conversation yesterday with either you, someone on that side, or someone close to this side, you're anticipating one of the things we're going to discover, which is that, well, now I have a whole bunch of other anti-symmetric, higher rank fields in the theory. What do I do with those? That's a clue. So that's where we're going. Yeah.
Just because I was wondering about the physical quantity, so you have spin. This is bosonic side only, right? So you have spin 2, spin 0, and a bunch of things, which is kind of topological, I would say.
Well, I think I just answered the question. Yeah. Okay.
Professor?
Yes.
Sorry, so you said that you cannot couple those Ramon fields in the string sigma model, so then how is it that you can write down those?
So as I said, one way of deducing it is to simply know the kind. Remember, we have two very specific types of supersymmetry in 10 dimensions: the type 2A and the type 2B, right? The chiral one and the non-chiral one. And so one way of deducing how to complete those actions is simply to demand that they have those supersymmetries. Is that, yeah? It turns out that you can classify things in 10 dimensions so much that you're actually done. Those are the only supergraphs using it right now. There is other technology on the market which, okay. Once you've done that, you could go back, right, and say, every term in here corresponds to something I can get as an interaction in string perturbation theory. Okay, and so you can also check consistency that way. But that the quickest way is to do what I just said. So it turns out to be consistent with everything you can do at the tree level string theory. But yeah, and then I think people like Nathan Berkowitz and others have been developing more advanced techniques in string theory that attempt to handle Ramon fields at the world sheet level more fundamentally. But I'm not really sure where the state of the art is in that technology right now, so I won't talk about it. Okay. Okay, so how are we going to tackle this this puzzle that came up at the end of last time, right? Which is that, well, clearly this can't work for open strings, right? Because the fundamental thing that actually made this work is the fact that I had this conserved quantity called winding, right? The fact that a string can wind, and it gives me this nice integer w, counting how many times the string can wind around the circle, and then that w gets exchanged with that other conserved quantity n, the momentum in that compact direction. Clearly that can't work because an open string has ends, right, and tension. So if I just step back, it's going to unwind itself, right? It's not a conserved quantity. Okay, so something must go wrong, and then I sort of threw out the glib idea at the end. Well, maybe we could get it to work if we kind of just hammered those ends down and sort of pinned them down, just stay there, okay? And that's a clue. But let's discover it. Let the theory tell us what it wants to do. So open string T-duality. Actually, let me make another remark before we let the theory tell us what it wants to do. On the one hand, what I just said is true. The string has ends. On the other hand, there's this. This is my favorite demonstration of today. So, okay. So, which one of those is an open string and which one is a closed string? The right one is which? Okay. Do we take some bets? Right. The point is that you can't tell. The point is that the only difference between an open string and a closed string are the ends. So somehow, when it comes to study T-duality for open strings, the interior of the string should know about this thing that it wants to keep going back to 10 dimensions, and then the ends are doing something different. So the answer, whatever it is going to be subtle. Okay. So with that in mind, let's proceed. But yeah, and you were right. I had drawn. You probably saw. Right. I drawn that. And okay. Good. Okay. So here we go. So how we're going to do this is I'm going to say that I can go back to the basic worldsheet conformal field theory, where our main observation was that I can simply write down the theory on R prime, the dual theory, by working instead not on x9, but what I'm calling the coordinate x9 prime, where I've put that right-handed parity swap in my definition. Okay, so and then the theory doesn't care, and I can also define this for the open string and just see what happens. Okay, so let's do that. So let's go back to mode expansions. Okay, and so I have x mu z bar is x mu z plus x mu z bar. Okay, and let me so let's just write this out again. Now we have in mind the open string, and again I'm just going to make a split in the zero modes representing position, just to make the point. Half, and then there's all of the oscillator stuff as before, and then x mu z bar x mu 2 minus x prime mu 2. Right, so what I've done, just for fun, I split things. I've introduced this thing x primed mu over 2. I added it in here and subtracted it out here. Doesn't matter, because so far in everything we're doing, this thing, it would just cancel out in our definition, and it'll have meaning shortly. Okay. So what I'm going to do now is put x9 on a circle just as we did before. Right, and so what I should do is I should write out, so I could write x9, just write these out again with a 9 on, let me not do that. Let me instead look at what would be x9 in our putative dual theory, which would be x9 of z minus x x9 of z bar. Right? So if you like, I'm doing an experiment. Inspired by what the closed string sector told me, I'm going to just go into the open string theory and see what this quantity is doing. So there's the difference. So let's actually just write that out. Again, the oscillator stuff is not so interesting, so I won't write it out. So I have x9 primed minus I alpha primed p9 log of z over z bar plus oscillators. I guess that maybe I'm getting to it. Should I not proceed further? Let me go sideways because I'm worried that you won't all see it. So I have x9, sorry, this is little x9 primed, plus, I'm going to write this out in two ways. I have 2 alpha primed p9 sigma plus oscillators. Okay, that's the log of the ratio. Sigma, recall, is telling me where I am along the string. Going from 0 to pi. And so that's kind of nice. Okay, and then because we have momentum on a circle that's quantized in units of n over r, and so we can write finally this. Okay. So I'm going to do one more step in a moment, but let's just admire our calculation. And then what I'm going to do now is I'm going to ask a similar question to what we asked when we did the closed string, right? Which is where we came in with winding. We said, what happens if I take sigma from 0 to 2 pi? Well, I should be able to go around the circle in space-time some w number of times, and we did that on the x9 coordinate. Okay, so I can ask the analogous question here, which for the open strings is where are the ends, right? Where is sigma equals 0 compared to sigma equals pi? You know, where are the ends of the string? So let's ask that question. Okay, and so x9. X prime 9 at sigma equals 0. Okay, it's not something we can look at. Let's actually just worry about the difference because that's the important thing. Right, this is where are the ends. Okay, so I can do that computation. Okay, so I just handily gets rid of that x9 prime, which is just keeping track of some center of mass, which we don't care about so much. And I have 2 pi alpha primed over r n, which I'm going to write as 2 pi alpha primed over r, we know is a very nice natural quantity. It's the inverse radius, it's the r prime. So let's call it r prime. Okay. So how do I read that? I read that formula as the following. The endpoints of the string in the 9th direction are in the same place. Right? Because remember, x9 is periodic. It's a circle of radius r prime. Okay? So 2 pi r prime or n times 2 pi r prime are all the same place. Yeah? So I've discovered that they're in the same place, which is interesting. They're in the same place. But really, let's be careful. They're in the same place in the 9th direction. Yeah? They're not in the same place in any of the other directions necessarily. In x prime 9. So let's emphasize that because that's interesting. Okay, and they're in the same place up to an integer. They could wind. That same place could be having gone round some integer number of times, and then ending up back in the same x9 position. So, just as we did last time, it makes sense to try and think of a way of drawing this in a useful way that organizes our intuition. And so, let me do it this way. So here is the x9 primed position. Okay, and what I want to do is keep track. So right, and then I have 0. I have 2 pi r prime. I have 4 pi r prime, etc., etc. Right, going on further. So basically, I'm just repeating this unit cell space-time over and over again. That's the x prime 9 circle, x9 prime, which it's the circle. Okay. And then what I'm finding is that I have an open string, which deserves to be a different color as it has been all along. Except there. Draft. These things are important. I know you don't think so. Yeah. Color coding everything helps me keep things straight. Okay. So for example, let's say one was at the origin, and just for the sake of argument. Then the string does whatever it wants in the interior, but it must still have its end in the x9 direction. It's the same position in the x9 direction. Or I could also draw that, right? That would be n equals 1. Yeah? And the first one was n equals 0. Okay, so what we're discovering is that there's a really nice language. It's a really nice language, which is becoming more and more geometrical. And so here's a nice way of drawing this. I also want to have a picture of what all the other endpoints are doing. And the point is that all the other endpoints are doing whatever they want to do in the remaining directions, the remaining spatial directions. So I can represent that by just saying, well, transverse to all of this, at 0 here, is the plane representing all those other directions, and the open string endpoints. So so now let me draw this. Let me draw this differently. Let me draw this to show you that those open string endpoints can be in other positions in that transverse direction, in all those transverse directions, but the same position. So they're stuck on this plane. Okay? And then there's another copy of the plane here. That represents one of those having wound once around the circle before coming back. Are there any questions about that picture? Because this is it. This is, you know, the main geometrical language that we use. These things are, right, the title of the course, D-brains. So if you don't get this, then, yeah. So are there any questions about that picture?
How would it change if you compactify, not in a circle, but in...
Let's stick with circles. This is longer. Yeah. Let's stay with circles for now. Yeah.
Those planes are identified, right?
Yes.
They're the same.
Yes. We're going. So far we just have one D brain, and let's understand it, and then I'll show you how to have an arbitrary number. Any questions? Everybody have? Okay, everyone's going, oh, come on. That's it? But no, this is really important, because this really, once you start geometrizing a number of the things we've been doing, it really is going to help you think in completely new ways about old stuff, which will produce new results. So this is, in the language then that we're going to use, we're discovering something interesting. We're discovering, first of all, that one of the directions, right, the boundary condition on the strings is that they must be in a fixed place, right? That's what we would call a Dirichlet boundary condition, yeah? So hence D-brains, right? The D comes from Dirichlet. So we have, so let's write it here, we have a Dirichlet boundary condition BC in X9 prime. Right? Paul Therese, this is in the X9 prime direction, not X9. You know, in all the other directions we have Neumann boundary conditions. Okay? In X else. Okay? So, what else did I want to say about this? So this motivates the name D-brain. It's some extended object, which in a moment we will see deserves to be thought of as a brain in terms of a dynamical object that can do stuff. And then D is the language. So the additional piece of notation that people tend to use is to count the number of directions that are Dirichlet, that are Neumann, actually telling you then how many, you know, what is the dimension of this extended object? Is it a membrane? Is it a string? Is it some higher dimensional object? In the language we've been using here, this is a D8 brain in the sense that there are 8, okay, there's one transverse spatial direction, one Dirichlet condition, or if you like, 8 Neumann conditions telling you what the world volume of that object is. So this is the world volume of the object. Or really, this is the spatial part of it. And it's 8-dimensional. So it's an 8-dimensional object we've just defined in that way. Are there any questions about that? This is the language.
Yeah. Sorry. The endpoints of this string are freely moving on the first plane?
The first plane is also the second plane.
Ah, okay. Yeah.
Right, so yes.
No, but these points could move around.
Yeah. Everything you learned about open strings from Barton, right, is true. I don't know, did he do D-brains? No, right, so you probably were finding solutions with string endpoints, doing all kinds of things, right? Those were all Neumann boundary conditions, and they were all in this, in that plane. Okay, here's a way of thinking about what you were doing with Barton also. You had Neumann boundary conditions everywhere. So if you like, the entire space-time was, if he was actually doing bosonic string theory. Yes. Okay, but let's imagine he was doing everything he did for 10-dimensional string theory. Then he was working really secretly on a D9 brain, or if you like, a D25 brain. In other words, all the spatial directions in the whole theory had Neumann boundary conditions. The string endpoints can be wherever they wanted to be.
And there is some constraints in the length of the string. I mean, it's strange or something like that.
It can what?
Yes.
Yeah, it can do everything it always did before. Yeah.
Yeah.
I've only just given you this one constraint. This is the solution to the conundrum we had, right? Where we said, well, we can't, T2RT shouldn't work in the same way as it did for closed strings because there's no conserved winding. And the get-out clause there would be, well, if we could trap the ends, okay, so we trap the ends, right? The other objection was, well, something like that should work because the interior of the string should always remain 10-dimensional because of this, and yes, right? So the interior of the string is just still in the full 10-dimensional theory. Yeah, there it is. This black line I've drawn is not in that plane. It's just the ends are on the plane. That black line I've drawn is wherever it wants to be in the full 10 dimensions. So that, I hope, completes our, you know, those are the answers to those things we were conjecturing at the beginning. So, you know, so at this point, you know, that's the language that gives us the realization that we should think about these geometrical objects, D-branes, You can see I can continue doing this. I can say, let me take the eighth direction, right? Put that on a circle, okay? And then rewrite the theory in terms of the x8 prime direction, okay? And what you would see then is that I have two transverse directions in which I have a Dirichlet condition, and then the remaining ones are Neumann, and so I would call that a D7 ray. I have a set. Was that your question? Yeah. Okay. Right, and I can just keep doing that. I can keep doing this all the way down to where I have no extended directions, and that would be a D0 ray. That would be some sort of particle. Yeah. And so yeah. So we're not done yet because we're going to see a whole bunch of other things that connect to some of the other observations we've made. But this is sort of the fundamental observation that I want to make sure that you're all happy with before I move on. So, yes.
Up to now, the x prime is, what is it in terms of the open string?
It is that. It's a perfectly legitimate thing that I can define in the conformal field theory. So why not?
But it is some kind related with the real x9 of the space-time.
Casting doubt on the legitimacy of the x9 prime direction, young man.
The idea we have previously of the x9, which was...
It's the dual, so let's go back to the observation we made yesterday. The conformal field theory does not care about space-time as much as we thought it might, right? It's saying you can put it on a big circle, put it on a small circle, I don't care, it's the same theory, okay? And so we started out by saying, look, we have the theory written with everything in terms of these x's, right? Take the bar and the z bar direction and add them together, okay? And bang, we did that, okay? And we said, this is a string theory on a circle. Now we realize we could have written the theory with exactly the same physics by swapping that sign. And it would just be telling us, if we chose to have a space-time interpretation, we just be telling us that the theory is now propagating on a circle with alpha primed over r instead of r. But it didn't care. It's the same theory. It's a duality. Yeah? And so now we go to the open string sector, and again, the conformal field theory doesn't care. All I'm doing is I'm saying I'm adding in some Dirichlet boundary conditions, whereas I just for some reason was doing traditional open string theory with Neumann boundary conditions. And why did I do that? This is a failure of imagination, if you like. People did actually do it, they just didn't realize what it meant geometrically. And so you're just doing more boundary conditions, more choice. You're just doing the other boundary condition, which is also completely consistent with everything that makes string theory a good string theory. Okay, well, I guess people understand this all fully, so I'm going to move on. Okay, so we have, excuse me? Okay, yes, we have 21 minutes. No, it's important. And I need every minute I can get. And so I want to now, well, you can guess, I think, already where the other brains are going to come from. Okay, which is that essentially all I was talking about. Actually, maybe you don't want to run ahead of me. So far, all we did, remember the open string sector then, the massless spectrum, right, has this space-time field, includes the space-time field a mu, right, which came from that, right? And this is essentially some U1 gauge field. In space-time. But we know actually that the full consistent open string theory actually has, can you help me? SO32, right? Okay, so there's a lot more stuff, and that came from the Chan pattern factors that we talked about. So essentially, the discussion I gave you just now hasn't really included the Chan pattern factors. Essentially, it was just talking about the U1. So there's the clue for how we're going to have more brains. We basically have more gauge degrees of freedom. So let's do that. Okay, so let me see if I can just decorate my calculation a little bit. So first of all, let me first go to a useful, simple place in the moduli space of possibilities, where so I compactify on a circle, okay, but I include a Wilson line in that compactification that brings my SO32 down into the maximal abelian subgroup. Okay, so this doesn't mean that this is all I can do, but it's a nice starting point, and then we'll see how to go back to the full SO32 shortly. Okay, so let me explicitly write down. So compactify. So we're starting again. This is the same calculation. But I'm just going to show you whether things change. So compactify on x9. Sorry, compactify x9 on circle. Radius r. That's what we did before. But radius r. Now include Wilson line. Breaking SO into down to 1. Okay. All I mean is that I'm going to pick a particular component of the gauge field in that direction, A9, A subscript 9, to be something. And in the language that, in the normalization that I'm using here, I'm just going to write the obvious diagonal matrix. Right? That does that. Okay? I guess 16. Yeah, right. Which is you know, sorry. We'll keep that. And so okay. Okay, well, okay, let me just, I'm going to have to, I think I don't need, this part of the calculation is more or less going to be the same. Yeah, it's going to be exactly the same, so I'll erase it. So the point is that if I were to actually write, continue the story, right, I write something like this, right, the path ordered exponential, right, where it has some charges, a thing that's charged under A9 with some charge Q would have a contribution of that sort. Let me then just be explicit. This would be just the thetas that show up here. Okay. Well, the point is that the things that are charged under that U1 are, of course, the ends of the string. Okay. And so the ends of the string in the normalization we're using are unit charge. And so how is that going to change things? Well, we know exactly how that's going to change things, right? Happily, I alluded to this already earlier, right? The fact that I have some charge particle of charge Q, I had it as E before, couples to a gauge field in this way, okay? And that is, what in undergraduate physics you would have written down before you wrote down the next step. You probably were studying charge particles in canonical quantization, and what you know is that just shifts the momentum of the particle, right? Essentially, remember, electric field is in canonical quantization. It's just another component of another additive piece to the momentum of an object, and so indeed, our momentum in the ninth direction, instead of being P9, is now instead of being N over R, right? It's shifted by if I do this right, the charge times theta over 2 pi r. As you can see by ask for single valid, go back and ask where did this come from? Single valuedness of the wave function as I go around and so on and so forth. You would pick up this additional piece. So in our other notation, where I have a string with charges I and j, okay, sorry, not charges, with ends I and j, that notation from last Saturday. This would then have some momentum which goes like N over R, and then I have the following. I have the 1 over 2 pi R. I have one end sees a positive charge, let me pick it as the I end. One end has a negative charge, which I'm going to call the J end, right? Because that's how we built the Chen pattern factors with these Hermitian lambdas. And so, bingo, that's what I need to know how to complete this calculation. Right? Because up here, I replaced P9 by N over R. But what I really should do, going through the calculation again and looking at what's the condition on the momentum for the open string with ends I, J in this Wilson line background, as I go around the circle, I should write that for the momentum. Yeah? And then I should interpret appropriately. So I go through and I write this for the momentum, and now remember that momentum business became a statement about position, right, in the dual picture. So similarly, I now have some additional information about position coming from this extra piece. Does the logic of that make sense? Good. And so now we see that we have some new positions at which we can put things. And that's great because that's telling us we have more brains. Sort of a Halloween statement. Zombies. Okay. Okay. So if I recompute this, then I have this. Let me just rewrite this. I have 2 pi n plus, in the language we've done here, I guess, yeah. So the way to read this then is that the ith, the ith endpoint in the dual direction is at position is given by r primed times theta I. or because this will be useful for thinking more generally and answering, at least in part, one of the questions that was about the more general case. If you like, it's the A9 component. Okay, here's the language. Okay, so T-duality in the closed string picture exchanged two important sectors, right? It exchanged the winding and the momentum of the string. Okay, in the open string, so that's still true in the open string dictionary. In that, with the caveats we've said before, because certainly the open string theory always has a closed string sector. The interior of the string, if you like, still knows about the 10-dimensional space-time, so it remembers some of that picture. But if you like, we have a new piece of language in our dictionary that says the positions of the ends of the string now are dual to information about the gauge field configuration. Right, so this is A9. This is the what we thought of as part of the 10-dimensional gauge field. Yeah, A mu in general. That information tells us now information about if I T-dualize in a direction that has some gauge field turned on, it's going to tell me something about position in the dual theory. Yeah, so that's a really important piece of the dictionary that we should come away with. So are there any questions about that? This leads naturally to the realization that D-branes are truly dynamical objects, right? Because, what do I mean by dynamical? There should be physics governing where it is, its position, right? It shouldn't just be at some fixed place. Right, now we're seeing that essentially the transverse position of the brain is part of a dynamical field that we already have in the theory, which is a gauge field. So gauge theory information actually is translating into dynamical information of extended objects in the theory. So D-branes are dynamical objects. They're not just sort of, you might have thought they're just boundary conditions and it's just telling me there's some hypersurface that's fixed in space-time. But no, it actually can move and wiggle a little bit, and that wiggling comes from the modes of the wiggling of the open strings. Right, so it's kind of this interesting situation where I have this object that's defined by the endpoints of where the endpoints of the open string can land, right? But the open string can fluctuate, right? And some of those fluctuations we are familiar with. It's the gauge field that the open strings tell you about in space-time, okay? And the internal components of those gauge fields in that transverse direction are telling me exactly where that D-brane is. It's not exactly in some fixed position. It's wiggling around because that's set by this. And so, yeah, it can change its shape, right? Think about how it can change its shape. Well, in general, a gauge field is some function, A mu is some function of all the space-time fields, sorry, all the space-time directions, right? Some complicated function. So if I look at the x9 direction, in particular, and that, as we've learned, is some instruction about where the brain is in the 9th direction, that instruction can vary over the rest of the x's. Right? That's an instruction not just to have a flat plane, but some plane with some non-trivial shape. That non-trivial shape is given by that dependence that the gauge field has. There's a huge amount of really, really nice organizational power that is in this language, right? And it was sitting in open string theory back in the 60s. We just didn't look at it the right way. So it's not like I've added anything to the theory, or it's not like Polchinski and his collaborators added anything to the theory. They just looked at it in a new way and realized that there's a whole bunch of content there that we've not been turning on, not been observing correctly. Does that make sense? sorry, not been observing fully. That people hadn't done anything wrong, they just hadn't done enough. Okay, I just realized last night that almost within a month, it's 20 years since Polchinski wrote his paper realizing how D-brains are important in a lot of the string theory discussion that was going on in the 90s. So it's kind of an anniversary, an important anniversary. I heard from Joe last night that he completely forgot. Anyway, it's really important. So I have 4 minutes left. I'm going to start setting up how we move forward from this. But are there any?
Sorry, how did you
important.
get this last equation?
Which?
This last equation, x9 prime equals theta I times r.
Yep, it's here, right? This equation?
No, this one.
Well, it's the same equation, right?
Same equation.
Right. This is telling me where one end of the string is. This is telling me where the other end of the string is. This part is just the part we had before, which is just saying, without that, it's just here. Yeah.
Okay.
But now I see I've shifted it. So these theta. Let me draw the diagram. Thank you. I should have done that. Right. So now, if I read this, I have some additional position, right, which I would call theta r primed, at which I should draw another plane, and this is going to get really messy, so let me change color. Now I draw another plane located at that position where that brain is. Yeah? And in fact, I can draw 16 of them for the full SO32 10-dimensional type 1 string theory. So, in fact, there's 16 D-brains lurking there. Going back to our other language, right, we can go back and say secretly the original 10-dimensional type 1 string theory with SO32 gauge group, secretly we were really actually studying a theory of 16 D9 brains, where D9 means they were filling space. We didn't realize we were living in the world volume of the brain. But now we've made them, now when we T-dualize, we can sort of step aside from them and look at them. Whereas before, we're always inside them in the dual picture. Okay? Okay, so yeah.
What do you mean by included I know that that's the definition of the what's the picture?
In this language, it's extremely simple. It just says this is, I pick a particular configuration of the gauge group. Right, I mean, right? But it's pure, it's lambda d lambda, so it's actually pure gauge locally. It's meaningful because I have non-trivial topology. I integrate around the circle. Yeah. Okay, so okay, I just realized that I'm in good shape to tell you, at least in words and as an exercise before the next lecture, and let you convince yourself that it all adds up correctly. But let's not worry about the full SO32 because there's some additional features there. There's the unorientability and stuff which you should still be worried about. Let's just imagine we were just doing some UN. Let's say U2, right? Which we had then broken down to U1 squared, right? So if you like some subsector of the theory, let's not worry about the full thing. Then I would have discovered that I had two brains. And there they are. Okay. And remember, I always get to draw copies of them, but that's not because why? I could forget. Okay. And the point is now I have strings that can stretch between these two brains, as well as strings that can stretch between the brains themselves. It's long, but yeah. So I have now all these different sectors. I have strings that can do that, and I have strings that can do that. Okay. If you think about it, the fluctuations of those strings then will be U1, just usual U1 gauge theory. Yeah. the mass spectrum will still give me the usual massless field representing a space-time U1. Okay, I heard a beep. I think I'm out of time. Which I would, at least for the 9 transverse directions, right? 0, mu goes from 0 to 8. I still think of that as a gauge field. There's some new stuff though, because I can also have strings that stretch from this brane to the other one. Yeah. So what are those? I mean, if you think about that, if you think about it, those are massive fields, necessarily because they're stretching some distance and there's tension in the string, and so they should have some mass. Okay, and what are those? Well, if you think about it, those are precisely the missing fields. If you like, the massive fields I would have gotten from Higgsing this down from this to that. Okay. And so I'll let you think about where the other fields are. Count them up. And remember that in this sector, these strings are oriented. Okay, I've kind of done it now, right? Okay. There's strings, there's these strings, there's those strings. Those give me the 2 U1s. But there's strings stretching that way, but there's also strings stretching that way. Okay, and if you think about that, if you moved those, this is my last sentence, if you move these 2 branes onto each other, okay, so you reduce that distance to 0, then you would see 2 things happening. In the Wilson line, you'd restore a U2, because 2 of these thetas would have become 0. And over here, those massive stretch strings would become massless because they're now no longer stretched. And they precisely fill out the rest of the stuff needed to turn U1 squared back to U2. Yeah? So it's a really nice picture. Please play with it on paper and convince yourself that that makes sense. It's not an analogy. It's exactly a geometrization of how you would think about adjoint Higgsing some gauge theory. I'm done.
Questions or comments? You said that the brane is a physical object because the position is proportional to the gauge field, correct? So
yes.
Later you said that the gauge field is pure gauge, so this is not a problem to the argument.
Two things. One, the fact that it's pure gauge is, I mean, when I have non-trivial topology,
Okay.
that it can do something.
Okay.
So that's answer number one. Answer number two, that's a lesson for a much more general story as well, where I don't necessarily just have this simple Wilson line.
Okay.
That's a much larger piece of language. But yes, there's physics there because I'm on a circle.
Okay.
Even though I start with something that's.
Thank you.
One question regarding the closed strings T-duality.
Mm-hmm.
Is there anything special about R squared equals to alpha prime? Invariant T-dual invariant theory.
Exactly. And the answer is yes, 1,000 times yes. Those are in fact called special points of enhanced gauge symmetry. And I just don't have enough time to tell you all the wonderful things that come from that. But yes, it's a very interesting point in closed string theory. And the moduli space of closed string theory has lots of interesting points when you put you're on some, you maybe got a taste of it in George's class where you're on some manifold with interesting things going on, maybe some interesting submanifolds, and sometimes those submanifolds get to special points where the string theory just becomes really, really very stringy, very highly non-analogous to Kaluza-Klein and what have you, and that's again the simplest prototype of that is the string at the circle at the self-dual point. In fact, we have one of the world's experts who's going to tell you about dualities. I'm not sure he'll be talking about that, but he knows an awful lot about
One last question.
You said that you could break the group in various ways. But
Yes.
what means that you can do it one way? I don't know. What
It's,
those are different.
it's just telling you about different configurations of D-branes.
Okay. Theory is the same.
Yeah. If you like, we have this big theory with some large gauge group, and we have a whole bunch of stuff charged into that gauge group. As we know from ordinary gauge theory, I can write down many different gauge configurations corresponding to stuff I'm doing with the physics of interest. Now all we've done is we've realized that the string theory has a way of geometrizing all of that. And so now a lot of those choices just correspond to D-branes at different positions that we're, and you might want to study some situation where you have a D-brane here and then one 3 miles away for whatever reason. That's now some gauge configuration. It has a particular shape, that's some gauge configuration, and so on and so forth.
Are planes because you draw
Just like this blue one, I showed you that I could have some general surface. All of them, right? Because it's just the x dependence of this.
Okay, we can continue in the discussion session this afternoon. Let's thank Clifford.